Hello and welcome back to another HPP Innovation Week session titled Inactivation of Salmonella in Fresh Poultry by HPP. High-pressure processing plays a key role in reducing the risk of releasing salmonella-contaminated poultry products to the consumer market. In this session, we'll discuss how fat levels in fresh poultry and acclimation of salmonella in fresh poultry can affect the efficacy of HPP on pathogen injury, inactivation, and recovery during the product's refrigerated shelf life. Joining us as a panelist is Frank Sumargo, research technologist at the University of Nebraska-Lincoln Food Processing Center. Frank is responsible for conducting a wide variety of HPP pilot plant and testing services, ranging from product and process development, optimization, validation, and shelf life studies. Thank you for joining us, Frank. The floor is yours.
Thank you, Anthony. So, hi, everybody. Good morning. My name is Frank Sumargo. Together with Dr. Grace Donau, we are from Food Processing Center, HPP Research Group at the University of Nebraska-Lincoln. Today, I'm going to talk a little bit about my research on inactivations of Salmonella in fresh poultry by high-pressure processing. So, the outline of my presentations today will briefly go over the applications of HPP to fresh meats, and then moving on to regulatory requirements by government agencies such as USDA and FDA. And then I'll discuss the process validations research from our group at UNL, mainly on the efficacies of HPP at a different scenario. The case study 1 will look at the effects of food matrix and fat levels. Case study 2 will look at the effects of acclimation times. And then finally, we'll look at the microbial enumerations protocols, and then discuss the key takeaway from all this research. I'm pretty sure by now you all know that HPP is a cold pasteurization process. The treatment has been approved as a pasteurization treatment by a lot of government agencies such as USDA, FDA, European Food Safety and Health Canada. It's been getting a lot of traction in a recent year. In the meat applications itself, the HPP is estimated to account for 20 to 30% of all HPP applications. It is mainly used to inactivate pathogenics and spoilage microorganisms, so mainly for food safety applications and extending shelf life. It is only known to inactivate vegetative bacteria such as Salmonella, Listeria, and pathogenic E. coli. The typical parameters for HPP used in the meat industry, it's about 450 to 600 megapascal for 3 to 7 minutes. So how does it get a lot of traction, especially in the meat industry? If you compare it to a conventional processing such as heat treatments, the HPP is relatively good at maintaining nutritional and organoleptic quality of the fresh products if you compare to heat treatments. But still rendering a pretty good safety aspects by reducing the microbial loads to 99.9% and up to 99.999%. The typical shelf life extensions by HPP for raw products is 10 to 15 days, and for ready-to-eat products is 30 to 60 days. However, the applications right now is very limited to ready-to-eat products. That's because the color, the texture may appear slightly cooked after the HPP, as you can see in the picture on the left, on the right. If you look at the bottoms, those are the pictures of the HPP of the cooked breast meat. If you there's really no visible difference between the control and the post HPP on those two pictures here, and therefore these applications is mostly on a ready-to-eat products. However, this is the only pasteurization technologies available for raw pet food products and any raw food products right now. So the salmonella is very commonly associated with fresh poultry, and then any salmonella found in a raw meat is considered adulterant. The risk of getting salmonellosis from raw pet food is actually higher than raw meat for human consumption. Mainly because raw meat for human consumptions will typically undergo further processing such as cookings, and therefore it's really essentially this is a ready to cook products, whereas raw pet foods, typically you'll feed it directly to the animals, and therefore it's masquerading as a ready-to-eat products instead of a raw products. And therefore the kill step has to be done to alleviate the risk, and the kill step has to be mild enough so that it can preserve a fresh characteristic of the raw meat, and therefore the HPP comes in. So this is just to give you a perspective of how devastating the salmonella is. It's estimated 1.4 million people are infected with salmonella annually in US, causing about 400 deaths and over 2,000 hospitalizations annually. The loss of productivity due to salmonellosis is about 3.7 to 11.4 billion annually, and about 1/5 of salmonellosis is actually associated with poultry products, so it's pretty big chunk. So considering how risky the raw pet food products and raw poultry products, and USDA issues a Food Safety Modernizations Acts that require all ready-to-cook poultry products to address the food safety issues. According to FSMA, if the HPP is to be used as a kill step, it must be validated to confirm its effectiveness. The pressure, holding time, and temperature has to be documented to be able to show that the pathogens is reduced by 99.999% or a minimum of 5 log reductions of specific pathogens. The validation study has to be performed by qualified individuals, and it must include a scientific evidence to determine if the preventative control is effectively control the hazards that most likely to occur. So these flow diagrams kind of shows the typical processings in a meat manufacturing facility. We have in the production, when you start with the production line, when you make all the products or value added to the final products, and then it being transported in the cold storage, and then before to HPP. This is very common for the company that doesn't have in-house HPP and it has to transport to a toller surfaces. And then once it's get HPP, and then it will transfer it back to cold storage and distributions to a retails, and finally to a consumer to be consumed. So the time for the final packagings to the consumer being consumed, that's represent the whole shelf life. Now, if you look at the validation study has to match up with whatever that happenings in the real processing flow in a manufacturing facility. We started with the inoculations process. Typically, this will represent any pathogens that elude interventions in production facility that finally end up in your in the final product. So the inoculations process started with strain selections, which essentially just risk assessment on what microorganisms that are more pertaining to the products. And then the method of inoculations, and most importantly, the meat matrix has to be conducted on the sample on the products that you wanted to test for. And then when the products being transported to a cold to transportations and cold storage prior to HPP, this is the time that allows the microorganisms to actually become more sturdier to adapt to new environments. So if you translate it back to a validation study, this is a time where your inoculation study, your attachment time for your inoculations and the bacteria can adapt. So in the sense that the longer the transportations and the cold storage prior to HPP, that allows more time for these bacteria to get adapted to new environments, to build up a new community, and essentially it's become sturdier and become more robust in the meat matrix. And that's where our case study 2, we wanted to look at the storage time is. So finally, the HPP treatments, if we wanted to do the validation study, it has to match up as close as possible to what's happening in the toller surfaces or in a real processing facility. Couple of variables that we need to watch out here is the pressurization rates, the fluid temperature, the pressure level for sure, the holding times, and the decompression rates. Once it's get HPP, the pathogen inactivations, and now we want it to recover what's left in the product. So this is actually really the measure of how efficacy the HPP process is. 3 things that we need to watch out here is the plating protocols, the culture media, and the enrichments. And that's how we assessed the efficacies of the HPP and how much reductions of the microbes that it gets. So for the case study ones, we really want to look at the compositions, how it affects the high pressure processing, the efficacies. So we formulate 4 different formulations that are typical for a pet food industry. The S1 is just a regular ground chicken breast. In terms of the pet food, this is a very premium products where you essentially this is a human grade products, right? So in this study also we use this as a control, as a reference points to compare as we move toward more similar to a pet food formula. So the S2 is we substitute 10% of this regular chicken breast to ground chicken backs and racks. So now we're starting to substitute 10% of the premium products to byproducts in the poultry processing. And the S3 and S4 is really what a typical pet food formula is, where it's 100% byproducts of poultry processing. So the S3 is the ground chicken backs and racks. The S4 is essentially same as S3. It's just being deboned before it's being ground. So if you look at the typical formulations, comparing all these 4 formula, you can see the lipid contents is what's most striking. Is as you move towards typical pet food formula, you increasing more and more of this fat content, which is about 100% of byproducts is about 15 to 20% fat. So this is the methodologies for the case study one. We start with the selections of 5 Salmonella strains that we use for the study. The Salmonella strains is selected based on what's commonly found in the meat products. And then we grow it on a frozen. We grow it from frozen to liquid medium, and then we transfer it twice to make it more sturdier before we harvest into liquid inoculums. And then the liquid inoculums being transferred, being inoculated into meat matrix at a target of 10 to the 7 CFU per grams. And then we separate it out into 25 grams of small individual packs before we acclimate it for 24 hours. And then we hit HPP treatment them at 450 and 590 megapascal for 3 minutes. And immediately after the HPP, we'll sample it to recover the remaining pathogens in there, Salmonella. And then we also sample at day 1, day 7, and day 14 throughout the shelf life of the products. So if you look at the S1 ground chicken breast, you can see here the red line represents a control, untreated control. The level of Salmonella is pretty much stable from the day of inoculations until day 14. It didn't change at all. However, when you are starting to pressurize it at 450 and 590, it's starting to decrease about 4.3 logs at 450 and 5.8 logs at 590. So if you see there at 450, obviously it's not in compliance with USDA regulations of minimum 5 log reductions, and 590 it's in compliance with minimum of 5 log reductions of USDA regulations. But as you move to S2, as we put out more of these byproducts and we increase of the fat level, you start seeing that number starts to goes down from 4.3 to now 3.6, 5.8 to now 5.6. However, the 590, you can still see it's still in compliance with USDA regulations. Now, let's move on to the S3. Now it's 100% byproducts, and it's very typical formulations for pet food. And the numbers even goes down significantly. Now you got only 3 log reductions at 450. And 590 is just in the borderlines of being compliance with USDA at minimum of 5 log reductions. Now it's only gaining 5.15 log reductions. Now, when you starting to increase up the fat level to 27%, suddenly all the numbers start to dwindle down at 450 megapascal, now you only see 2.79 log reductions, whereas 590 it's suddenly you out of compliance with USDA. It's no longer minimum 5 log reductions. Now we only have 4.1 log reductions. So if you did a statistical analysis of this results, and you'll get significant interactions between pressure and meat matrix, which mean both pressure and meat matrix are significantly affects the efficacies of HPP. So if you look at the recovery rates over the 14 days of shelf life, if you just go back to the S1, you can see the number is actually pretty stable after the day 1, and then it's pretty much stays there until day 14 with very limited recovery rate. The numbers start to increase up when you move to the higher fat levels, or you substitute the regular ground chicken breast to byproducts. Especially at 590, you're starting to see the recovery rates is increasing, and finally at 27% fat, you see a really steep increase recovery rates at the S4. It's about tenfold if you compare it to just the regular ground chicken breast. Now, what we learned from this case study is somehow fat is providing a protective effects to microorganisms, not only to elude the first kill from HPP, but it also somehow provide a better recovery rates after the HPP treatments. So if you do the counter plots of these recovery rates for different pressure and different lipid contents, you can see here the blue level, the blue color here. It's considered really low recovery rates and nothing to be concerned about. But as you move more towards the green and the orange color and the red is getting more intense, and they become problematic for the recovery rates. So at a 450, the recovery rates won't be problematic until it's about 22% fats in the products. However, in a 590, the lipids become even problematic at about 15% total content. So what does this mean to a pet food industry? As you can see here, 3 pet foods that we collected out there in the markets, the fat levels can be very ranging from 8 to 25%. So really we have to, before we design the validation study, we wanted to know the exact compositions. We wanted to see the fat level, and then that determines what parameters that we should use so that we can have appropriate lethality levels and control the recovery rate so that you'll be safe throughout the shelf life of the product. So in the case study 2, the methodology is pretty much the same as a previous case study. In terms of inoculum preparations, we start with growing salmonellas and transfer it to make it more hardy, harvest into liquid inoculums and inoculate it. Now, the purpose of this study is we wanted to see if the storage and the storage durations pre-HPP have any effects on the sturdiness of the microorganisms. So now we store it at 2 different time periods. We store it at 24 hours and 72 hours before we HPP them. So it's still HPP at 450 and 590 megapascal for 3 minutes. And then we immediately, after HPP, will sample it as the day 0. And then we'll sample it also at day 1 and up to 21 days. So as we can see here on a day 0 results, if you just look at the trends, 590 versus 450, of course you got more kill at 590 because you pressure it in a higher pressure. And then if you compare just the 24-hour and 72-hour and a day 0, there's really not much different there. I'm sorry. There's really not much different there in terms of these two, 24 hours and 72 hours. However, you're starting to see at 72 hours, you start to see the spread of the data, which means that we recover more of the salmonella cells at longer periods of acclimation times. So and the effect is more pronounced at 450, and now you're starting to see at 72 hours, the reductions is starting to decrease if you compare it to just this 24 hours. So the general trends here is with more pressure, you got more kill, which is kind of givens. However, with the longer acclimation times, if you compare 24 hours to 72 hours, generally you see a less reductions, which means a less HPP efficacies. So now if you look at the day one results, the trend is even more pronounced. At 590, you'll start seeing this. If you compare this 24 hours and 72 hours, you start seeing a really big spread on 72 hours results, meaning that we recover a lot more cells compared to just 24 hours, which means the pathogen is actually recovering is better at 72 hours. Now at 450, this is suddenly, if you compare just 24 hours versus 72 hours, and then this is a significant difference, statistically difference between those two sample time, which means that at 72 hours, really you significantly reduce the HPP efficacies, and the trend is pretty much the same, where you have more pressure, you get more kills, and then with longer acclimation time, you essentially decrease the log reductions. And then another thing that we wanted to note here is if you look at the result from day 0 to day 1, you're starting to see that you will recover a lot more cells in day 1 post HPP, meaning that the log reductions is actually lower in here. So a lot more sublethal injured cells in the HPP is starting to come back, and we're starting to plate more of these sublethal injured pathogens that are previously not be able to recover on the day 0. So essentially at this study also, we conclude that day 1 provide a more, day 1 plating provides more conservative estimates of HPP efficacies. So in a case study number 3, if anything that we learned from the other 2 case study is that the HPP is really not, the kill is not instantaneous, meaning that it will sublethally injure the microorganisms until it won't be able to recover anymore, and then eventually to cell death. However, if you plate right away after the HPP, you given no time for the bacteria to recover, and then versus if you plate it a day after. So that's why the day after you always get a higher recovery counts and the lower reductions essentially. So in this case studies 3, we wanted to see what plating methods that are better to recover these sublethally injured cells. So the methodologies is the same in terms of inoculum preparations and sample preparations. The only difference here is now we plated in 4 different plating media. The first one is XLD. This is a selective media for Salmonella, so it's only recover healthy cells. And then this C2, C3, and C4, these are all known to recover different plating methods that all known to recover a healthy plus sublethally injured cells. The C2 is modified TSA, the C3 is thin layer agar, and then C4 is overlay methods. So these are all known to recover both healthy and sublethally injured cells. Just a little bit of reminder, if it reductions, it's 2 log reductions mean 99% reductions, and 3 logs mean 99.999%, and so on. So to estimate the injury, if you think about the discrepancies of the cell counts between all these 4, if logically the C1 has to be the least among all these 4, because it's only recover a healthy cells, right? C2 will recover both healthy and sublethally injured. So if you subtract the counts that you got from C2 to C1, you got the estimations of the injured cells, right? Another steps that we do in the case study 3 is the enrichment step, which is assuming that you don't get any feasible colony in after the post HPP process. Do we just assume that we completely kills off the pathogens? Maybe yes, maybe not. Maybe they're just really, really weak that we won't be able to recover on the plates, or it's less than our detectable limits, which is 10 cells per gram, essentially. So if we enrich it, give it more times and media to recover, or give it more or less than those cells that less than detectable limits, eventually it'll show up in the plate as a positive or negative, as a qualitative assessment, right? So we did these enrichment steps where we enrich with a media for 24 hours, and then we put a selective supplements, statithionates, to it. This is a very selective for salmonella, and then incubate it for 24 hours before plate it to XLD to get this positive negative counts. So any positive counts means the cell is below the detection limits in 1 to 10, between 1 to 10 cells per gram. Any negative mean really there's absence of salmonella at all. So we only do this for 590 for samples that treated with 590 megapascal for 3 minutes. That's because and 450 and 300s will still be able to recover it. So if you look at the log reductions results at day 1 post HPP samples, the two-way ANOVA kind of shows the main effects of pressure and culture media is significant. So again, with the higher pressure, you get higher kill. This is kind of given. But what's interesting here is the culture media, when you plate it on XLD, TLA, thin layer agar, and overlay, they have a similar counts. But the XLD is significantly different from modified TSA. So what this means is somehow the modified TSA recover significantly more cells than XLD, which means that our hypothesis is right. The HPP, when you plate HPP, post HPP samples, you have to let the sublethal injured cells. You also have to count for those because those are eventually they're not death. They just so injured that won't be able to survive. They won't be able to show a feasible colony on selective media. So from the enrichment results, we also confirmed that all 590 megapascal tested positive for salmonella, which means that when the HP, even at 590 megapascal for 3 minutes, we'd not be able to completely kills off the salmonella. Some of the cells is just below the detection limit between 1 to 10 CFU per grams, or they're just really injured enough not be able to culture in the plating method. So this is the sublethal injured cells results. We only be able to do this on 300 megapascals because at 450 and 590 there are so few samples that shows be able to shows a feasible colony. So really the results is not so apparent. And this results kind of shows that the modified TSA are higher at estimating a sublethal injured cells if you compare it with overlay and TLA, but still somehow this results still shows that we still be able to recover a lot more, about 13 to 16%, about 10 to 16% of injured cells after the HPP that we won't be able to recover if we just plate it on selective media. So the key takeaway from all this study, is there's really no one shoes fits all studies. Even if you find one papers in the publications and then you think it might be applicable to your products, maybe you have to rethink that thoughts, because the case study ones, we know that food compositions affect the efficacy of HPP treatments, lipid and fat, has an effects on inactivations and reductions of pathogens, and also the rate of recovery. So the result from one validation study may not be applicable to similar products if they are sufficiently different. From the case study 2, the acclimations, the storage time between the transportations and the storage before the HPP is really important to make these pathogens hard enough to kill by HPP. So assuming the pathogens are introduced during a manufacturing validation study has to account for these typical times to move the products. Long transportations and handling pre-HPP storage times may allows the pathogens to become more resistant, and therefore it reduces the efficacy of HPP. Also, on the case study 2, we found that the plating immediately after HPP it's less conservative than if you plate 1 day after the HPP, because you're allowing more of the subliter injured cells to recover, and then that's kind of more accurately represents your true lethality of HPP rather than you plate immediately. It'll give you a false sense. On the case study 3, because subliter injured cells can recover post-HPP, it's important to culture the media that can grow both healthy and subliter injured cells by using either overlay or thin layer agar. And the enrichment is kind of a proof that some of the subliter injured cells that may not be able to culture in the media may still, they're not completely dead, they just are below the detection limit, or they're just really injured, they won't be able to show on the plate. So lastly, I wanted to introduce the HPP Service Labs at UNL, and here we really customizes your study based on what you need. We provide a consulting, product developments, process optimizations, validation study, and shelf life study, and trainings and workshops. So we really tailor all the designs, all this validation study on your needs. So if you have any questions at all, please do not hesitate to contact either myself or Dr. Grace Denau at this email address. Thank you so much for your attention. Thank you so much for Hyperbarics for allowing us to show our research. Thank you for the opportunity, and then I'll give back to Anthony.
All right, thank you, Frank, for that insightful presentation. Aside from contacting Dr. Grace now and Frank Samargo, if you have any questions, also feel free to check out their website at www.fpc.unl.edu. You'll be able to find more information about their food processing center and the services they offer there. Well, that wraps up our session. I want to thank you all for joining us, and we'll see you in the next one.